Hello, my name is Guillermo Zavala and from Pontificia Universidad Católica del Perú, and I will present the paper Implications of Nonlinear Shear Strength and Interface Envelopes of Reinforced Compact Sand Fields in Very High Earth Structures, a paper developed with Dr. Miguel Pando from Drexel University. As an outline, there will be a brief introduction, examples of very high mechanically stabilized earth walls and geosynthetic reinforced slope projects worldwide and in Peru. We'll discuss the possible implications of very high normal stress levels in the designs and the effect of these in the shear strength of the backfill and the interface friction strength envelopes, and then present summary and conclusions. As an introduction, in the past few decades, well-established geostructures as MSC walls and GRS slopes have been used widely, and these structures have grown a lot in height. This brings a lot of very high normal stresses at the bottom of the structure. So as a motivation, we'll discuss the possible effects of these high normal stresses on the shear strength of backfill envelopes, which actually have been really those have been well studied in the literature, and also on the backfill geosynthetic interface envelopes. These, on the contrast, have not been well studied, and you cannot find a lot of information in the literature. And we'll discuss the design implications of the curvature of these envelopes. So we have an airport runway in Sikkim, India. Well, we have a 80-meter structure. It's a mixed structure it has gabion walls and geogrid reinforced MSC walls with normal stresses well above 1 MPa. There's a runway extension at Charles Jigger Airport at West Virginia with a 1-to-1 geosynthetic reinforced slope with height up to 74 meters. Of course, stresses more than 1 MPa, a lot more than 1 MPa. That had a problem that actually failed a few years after constructions in 2015, and then it was reconstructed in 2019 using a lot of different geosynthetic structures like soldier piles and other stuff. Then in Peru, we have a lot of projects that are in mines, like the Cerro Verde copper mine primary crusher in Cusco, a 34-meter MSC wall with stress levels up to 0.8 MPa. Constancia mine primary crusher in Cusco, a 30-meter MSC wall with stress up to 0.8 MPa. Both of these support a lot of surcharge, 610 and 400-ton mining trucks for the primary crushers. Then the Toquepala mine primary crusher, that's a 28-meter and about the same stress levels. And Pampa Verde waste dam expansion is a little bit different because it used to be like an upper and lower MSC wall with an unreinforced slope for a waste dump. And then they had to do an nitrogen solution, which is to grow it up a lot more. So they made a geogrid reinforced slope up 41 meters of height, so they can put the waste behind. The possible implications of these high normal levels, especially at the bottom zones, where we reach normal stresses at more than 1 MPa. First of all, we're going to focus in two zones: a zone where there's the interface shear strength between geogrid and backfill, and then a second zone where it's just backfill against backfill, so just regular shear strength. Now, when we're talking about just regular shear strength envelope, we can see this classical study from Lee and City in 1967. There's also another study from Bessick and Clough in 1968. We can see that above 500 kPa of normal stress, we get this curvature, this curvature, and this study actually went almost to 4 MPa. And so we do see this curvature, and the way you take this into account when you run models in computer programs where you need a linear fit, then you just select some zones and do a fit of a C prime and apparent cohesion and apparent friction angle, and you start to change them with the normal stress. No, so you get those, but those are not really properties of the soil. We're just making a little numerical artifice, so you can capture that curvature. No, you're subdividing this strength envelope, so you can get lines. Here are studies on interface friction strength, but you can see that all of these that we have collected are much lower than 500 kPa. They don't even make it to 200 kPa. So that's why I'm saying in the literature there's not a lot of studies that capture this curvature. And here we can see the relationship between linear shear strength of an interface shear strength and the relationship between the curved surfaces, also from shear versus interface strength envelopes. There's a relation between these, and sometimes what you can do, you can pick the same relationship between the top linear interfaces and the bottom curved envelopes, and that might work, but not always, because sometimes it's a little different. Here we can actually see a study from the last case presented, which is Pampa Verde waste dam expansion, where they did tests up to 800 kPa. And what we can see here is that that we did find a curved interface of friction strength, the interface friction strength envelope, just by looking at this delta second of a phi ratio. Now we can see that this is reducing, which is indicative of this curved envelope. So we should actually, if we use this in a program, we should actually use that section, that subsection where you can get this fit of phi and c, and we can get in the program. So it's very important to take this curvature into account. A summary and conclusions, there are very high MSC walls and GRS structures that are common in the world and in Peru, and a few examples are presented here. The normal stresses in these structures are can be more than 1 MPa. Common design software assumes linear strength envelope and interface and linear interface stress envelopes. So what we should do, if we have a curved shear strength, which usually occurs, as I said, above 500 kPa of normal stresses, then we should use equivalent linear strength envelopes, so that we can capture that curvature. We also saw that interface friction behavior is studies are very limited for normal stresses of 1 MPa and above. So more studies are needed in these cases. So then when we have these curved interface strength envelopes, those equivalent linear envelopes are recommended unless the software can be modified so it can capture that curved envelopes, but that's not, as I said, that's not very common. Usually you need a linear strength. So if you neglect to take into account that curvature, then you can have unsafe designs. Why? Because the curvature means that there are higher normal stresses. A linear envelope will be overestimating that strength, and that's why you can get unsafe designs and possible failures. And then actually, if you have large projects, then you should do interface shear tests at those higher normal stresses. Those are highly recommended, and it's also ideally you should do those with project-specific materials, not with other generic materials. Okay, that's it. Thank you very much for listening to this presentation. These are our emails in case you have any questions.